Hello everyone, welcome to the ISMAR 2020 conference. My name is Alan Young from the University of California, Berkeley. In the next few hours, I, together with two highly experienced student researchers, will provide a tutorial on the topic of OpenARK, tackling AR challenges via an open source software development kit. Before we start today's discussion, please allow me to first introduce our team. I'm currently the Executive Director of the FHL Vive Center for Enhanced Reality at Berkeley. The center is part of the EECS department, which serves as a central hub to promote and coordinate the teaching and education of the AR/VR programs at Berkeley. I was previously the Chief Scientist at the Fung Institute, also at Berkeley, helping the Institute to launch two Master of Engineering degree programs in the areas of AR/VR and autonomous driving. Before that, I also served as the founding CTO and the COO at Aether Labs, an augmented reality startup based in Silicon Valley. I will be giving the first introductory talk about our OpenARK tutorial. The second talk will be given by Adam Chang. He is currently studying in the Computer Science Bachelor's program and is also a lead undergraduate researcher at the Berkeley Vive Center. Then the third talk will be given by Mohammad Kashavasi, who is a PhD candidate at the Berkeley Vive Center and the XR Lab affiliated with the Architecture Department. He has extensive collaboration with the industry to explore the interdisciplinary topics in AR/VR and architecture, such as with Autodesk and Facebook. Of course, a software system as OpenARK could not possibly be developed with only a few people. Many students from UC Berkeley have contributed to this system. Today, we will only have time to acknowledge a few lead developers from the past, including Dr. Joseph Mankey, now at Apple, Dr. Oladapo Afalabi, now at Microsoft, Bill Zhou, now at Facebook, Will Huang, who is running his own startup at this time, and Jie-Wen Lai, who is now at Amazon, and Johan Ramakrishna, who will be graduating from Berkeley by the end of this year. Two lead undergraduate students other than Adam we want to acknowledge also here are Wu-Jing Ku and Alex Yu. Several funding agencies have supported our project as well, including several research grants from the ONR, Intel and the NSF Joint Research Grant on XR, Ford University Research Grant, Siemens Labs at Berkeley, and the Berkeley Vive Center Sea Grant from our home center. Today's half-day tutorial will be divided into 3 parts. Each talk will be roughly 1 hour. The first talk will be introduction and foundation of 3D geometry, sensing, inference, and tracking. The second talk will be focusing on SLAM and 3D reconstruction solutions provided in OpenARK. The third talk will venture further into supporting development of deployment of high-level applications using advanced generative modeling in spatial computing. Each talk has been organized by the 3 speakers individually to have either several separate segments or 1 hour-long talk. During the segment breaks or our session breaks, most of our speakers will stay online to answer your questions. So please feel free to raise any questions during the tutorial, and we will try our best to follow up with your questions from our online interface. Also, the videos for today's tutorial will be also made available on our center's website at vivecenter.berkeley.edu. From our center website, you will be able to find our other exciting projects in the general areas of AR, VR, and AI and robotics. And you will also be able to find our educational programs if coming to Berkeley may be something of interest to you. For industrial partners, I would like to invite you to consider joining our industrial membership program, which we have provided more details on our center website as well. At the beginning of this tutorial, I think it is worth looking back in history and recognize that since Morton Heilig invented the Sensorama in the 1960s, the first virtual reality entertainment system, it has been 60 years. Later in the same century, Ivan Sutherland in 1968 created the first wearable augmented reality prototype. And AR, or more commonly known as holographic images, started to become a household name thanks to the genius creators of Star Wars movie in 1977, which showcased the use of augmented reality in a futuristic long-distance virtual meeting scenario via a piece of Princess Leia's holographic message. Today, we can say that this future world enhanced by augmented reality technologies is never more closer to reality in our daily lives. Starting from the commercialization of Google Glass that instantly captured people's imagination, our customers primarily have 4 distinct ways to enjoy augmented reality experience today. And they are see around wearables, with Google Glass as an example, see-through wearables represented by Microsoft HoloLens, AR on smartphones such as using ARKit or AR Core, and the escape room mixed reality type experience that mixed virtuality with reality simulations. To support AR applications to provide superior immersive experience, OpenARK is not intended to be jack of all trades, but focuses on providing a few fundamental solutions as an open source library that promotes community collaboration and reproducible research in the AR space. The areas ARKit is currently focusing on, including modeling background layout, modeling foreground objects, modeling user avatars, and optimization and sharing standards in mutual spaces. The library currently supports a selection of hardware and software. For the hardware, we have tested extensively on the 64-bit x86 processors. In the near future, we plan to further support ARM-based processors, such as the NVIDIA Jetson architecture. Interested developers may contact us to collaborate if you want to prototype an AR system using ARM processors. We are more than happy to reach out to assist you. Our library currently does not provide GPU acceleration though, and all algorithm implementations will be based on the CPU. Also, as an open source library, we have supported a host of depth cameras, starting from very early the PND cameras. Then we added the Kinect 2 camera class. Then the Intel RealSense D435i camera. Our latest development will bring in support to Stereolabs Z2 camera and the Microsoft Asia Kinect camera. In terms of the software environment, we have provided a very easy to install 64-bit Windows binary installer of the library. On Ubuntu 18.04, you can also build the library directly from source. OpenARK will also have several dependencies, just like most other libraries. The most fundamental dependency will be the OpenCV library with the version 3.2.0 or later. Other libraries we have included, including the Eigen version 3, Point Cloud Library 1.8, Boost 1.6.4 or later, etc. Also, it is very important to note that OpenARK, being a software library focusing on low-level computer vision and depth perception functionalities, there are many other topics that greatly affect the realistic user experience in AR applications, but we will not be covering in OpenARK. If you plan to adopt OpenARK as part of a commercial system, you will probably need to support of good solutions in the following areas, and they are near-eye display and optics, AR coprocessor acceleration, custom sensors, high bandwidth, low latency communications, 3D spatial sound, and the 3D UI/UX design. However, one type of sensing modalities, OpenARK does provide strong support for depth camera. Indeed, the use of depth cameras to support augmented reality has been the consensus among many AR systems today. For example, when I worked at Athere, we were one of the first to put on a depth camera on the top of a smart AR glasses. More recently, we have seen probably the largest proliferation of depth-type cameras on Apple's iPad and iPhone lines. Let's recall first, before the rise of depth cameras, 3D structures could be inferred using multiple views of color images. This is called structure from motion, or multiple view geometry. As shown in this demo video from the paper Building Rome in One Day by Samir Agarwal and co-authors in 2010, when a structure from motion system can have access to hundreds to thousands of realistic color photos, then 3D structures in the space can be triangulated. However, the downside of a structure from motion is also multifold. For example, structure from motion depends heavily on the good lighting of the environment, and the environment also must have rich texture patterns. Also, structure from motion solves an inverse computer vision problem, and therefore is expensive to run as real-time solution to infer 3D geometry. To better support the needs of immersive AR applications to acquire accurate 3D geometry of the environment in real time, other depth sensing solutions in recent years have been used in several successful commercial depth cameras. Next, we will briefly highlight two of them. The first is called Depth-from-Sterco. For a pair of stereo cameras, usually we will assume they are well calibrated, and after calibration, we may further assume their 3D positions only differ by a translation along the x-axis, denoted as the baseline B. If we are interested to know how the 3D coordinates of an image feature is calculated, here is the equation defined by the intrinsic matrix with four coefficients, AX, AY, and CX and CY. Then from the image coordinates U and V of these images, and assume a known focal distance f. And we will know that the 3D coordinates in the unit of meters represented as a vector, 3D vector of x, y, and z equal to f. And this is equal to the intrinsic matrix, the inverse, dot product with fu, fv, and f, where u and v are in the unit of pixel coordinates. Then look at the illustration on the right. Since the stereo cameras are aligned to only differ in position along the baseline x-axis, it is fairly easy to identify a match of two image features corresponding to the same 3D point X in space. Next, if we represent both the 3D coordinates of the first feature and the 3D coordinate of the second feature now in the same coordinate system O', and their coordinate difference only along the x-axis, written as x minus x prime, will be called the disparity. And according to the similar triangle relationship of this triangle versus this triangle, the disparity x minus x prime divided by f will be equal to the ratio of the baseline b divided by the depth z. Therefore, we have the calculation of the z value with respect to this 3D point in space is equal to b times f divided by the disparity. The second principle is called time of flight. The most direct use of time of flight principle is the LiDAR system, or light detection and ranging. This principle has been known to humans since the caveman era, where we know that we can estimate the distance between a human, a caveman, and a mountain by sound. And this distance between the human and the object that reflects the sound wave can be calculated by half the travel time interval times the speed of the sound. In LiDAR, this principle is used to measure the distance, but using the laser light instead of the sound wave. For example, during the Apollo 11 mission, NASA placed a lunar laser ranging experiment on the lunar surface, which then was used to accurately measure the distance between the light and between the Earth and the Moon. However, the time of flight principle also brings in the challenge of how to accurately measure the time. For example, let's assume a more modest distance of 10 meters. We know that the speed of light in the Earth's atmosphere is about 300 millimeters per second. Therefore, 2 times the distance of 10 meters divided by 300 milling will be about equal to about 66.7 nanoseconds. This is a very tiny fraction of time that will have required very accurate system clock. In most consumer-grade depth cameras, however, the measurement of time will be substituted and converted to measuring accumulated electric charges or phase shifts from the bounced back light signals. Due to the limited time today, we will not go further into details about how these principles are implemented engineering-wise, but we will provide a fair comparison about the quality of the depth data collected by Depth-from-Sterco and time-of-flight cameras. In the first video, we installed a state-of-the-art Depth-from-Sterco commercial system in the cabin of a car. And we want to capture how depth data may support 3D avatar virtual interaction inside the car. Notice that, to be fair, inside the car environment is one of the most challenging environments to conduct 3D sensing due to complex outdoor lighting, vehicle chassis vibration, potential high temperature, and close distance in a jam-packed small space. Let's first view the video And please notice that on the bottom right corner, we have superimposed the RGB version of the same scene in comparison with the acquired depth data from the Depth-from-Stereo solution. From this video, we can see that usually the resolution of depth images can be coarse than typical RGB images. More importantly, depth from stereo becomes ineffective when the stereo image source becomes saturated by sunlight or underexposed by low light. Finally, depth from stereo usually has limited range in short and long distances, which will create invalid depth data shown as many black regions in this video. In contrast, invalid pixel values do not exist or very rare in typical RGB images. We can compare the previous video in the same scene now captured using a Microsoft Asia Kinect camera. Asia Kinect uses time-of-flight principle to measure depth. Compared to the previous example, we can easily see that Asia Kinect in outdoor environment provides much better signal-to-noise ratio. And the generated depth images are much sharper than the depth from stereo system. Second, Asia Kinect is affected less severely by the sunlight and also works well under low light condition thanks to its onboard modulated time-of-flight light emitter. But same as almost other depth cameras, time-of-flight cameras also generate invalid depth pixels, already shown in the image, due to its own distance limitation. To summarize, when we design algorithms using depth cameras, the algorithms must handle the following situations specifically. Number one, we will need to handle coarse or more noisy depth data compared to RGB images. One common practice is taking smoothing of adjacent pixels in the 3D matrix space. And second, we will need to handle the existence of invalid depth pixels. In matrix representation, those invalid depth are usually denoted as zero values. As such, including zero depth pixel values in most of our calculation will be wrong. The correct way will be to write in your code to exclude these invalid pixels from the calculation altogether. In addition to the three depth inferencing approaches, there are two other popular used approaches, and they are called structured light and depth from defocus. Now let's put the 5 approaches in one table and go over under what circumstances we should consider or not consider these 5 approaches. First, structure from motion. This is the classical solution from computer vision. It is widely used in real-time 3D localization and visual odometry to estimate R and T, rotation and translation, of the corresponding camera sensor. And it also works well in large-scale reconstruction problem from big data photo libraries. Depth-from-Sterco is good for outdoor applications and has good trade-off between accuracy and cost. Its measurement tends to be more accurate on texture regions, such as regions can be actively created also by an onboard light emitter as well. On the other hand, structured light is more suitable for indoor applications, and it is also low cost. However, under the same scene conditions, Depth-from-Sterco and structured light both tend to be less accurate compared to the time-of-flight solution. Then for high-precision applications, the usual choice will be time-of-flight sensors, and they are particularly good for both 3D localization and dense 3D reconstruction. However, time-of-flight systems are more expensive and demand higher power compared to most of the other systems. And then they don't always work under the sun and need special design and hardware to work accordingly outdoors. Finally, if our camera mechanism remains conventional, we can still estimate depths using depth from defocus approach. It is commercially used to enable automatic lens focus adjustment for camera lenses, but it is not a good choice for 3D reconstruction and scanning in AR applications, because recovering the defocus or the blur function from images typically does not return a dense depth map, but only a sparse map concentrated around only the textured regions. Now we will pause our talk here and see if the audience have any questions. After that, we will proceed to discuss the second part of this talk.